Hello everyone, welcome back to this week's algebraic graph seminar. And first, I want to tell you, as next week, we will take a break because of the Easter Monday. And now today we have Dr. Wang to tell us about deletion-contraction for unified Laplacian and applications.
Thank you. Yeah, I'd like to thank the organizers for inviting me. I think actually this might be the first talk I've been invited to give outside of UBC. So yeah, I want to tell you about a vertex and edge weighted Laplacian. And my goal for today is just to convince you guys that this is all an interesting variant of the Laplacian. And I said vertex and edge weighted, but for this talk, I'm going to focus on vertex weighted. Every theorem that I put in here does have a version with edge weights. And let me also state that this is joint work with Farid, Aliniaeifard, and Steph van Willigenburg. My co-authors actually have very long last names, so I'm going to write our initials as AWBW. Whenever you see that, this could be us. Okay, so today we're going to be talking about multigraphs. For us, it's going to consist of a finite vertex set V and a finite edge multiset E, which may contain loops, edges connecting a vertex to itself, or multiple edges, more than one edge between a pair of vertices. And we're going to let EUV denote the number of edges from U to V, with loops contributing twice to EVV, just as convention. Then the degree of U is going to be the sum over all vertices V of the numbers EUV. So for example, here, U has degree 2. There are 2 edges emanating from vertex U. Degree V is 1, 2, 3. We have a loop, but that counts twice, so that's going to be 4 and 5. And EVW is, well, we have actually 2 edges between V and W, so that's 2, right? And that contributed 2 to this sum. Okay, there are some very simple graph matrices you can associate to a graph. The first one is the degree matrix, which is just the diagonal matrix with ith diagonal entry equal to the degree of Vi, once you label the vertices in some order V1 to Vn. So for example, if I label them V1, V2, V3, V4, this has degree 3, degree 2, degree 5, degree 4. I get the diagonal matrix 3, 2, 5, 4. And the adjacency matrix is just the matrix with ijth entry equal to the number of edges between Vi and Vj in that count I gave you. So for example, between V1 and V2, there's 1 edge, you'll see a 1 here. Between 3 and 4, there are 2 edges. So we have 2s here, right? And between V3 and itself, there's a loop, but we count loops twice. So it's going to contribute a 2 to the adjacency. Then the combinatorial Laplacian is defined to be the difference between the degree matrix and the adjacency matrix. So you'll notice here we have 3, that's the degree of V1, 2, degree of V2. This is 5 minus 2 because V3 had degree 5, had a loop, so we subtract 2, we get 3. And V4, degree 4. Here's a negative 2 because we had 2 edges between V3 and V4. Here's a negative 1 because we have 1 edge between V1 and V2. And when G has no isolated vertices, meaning no vertices with degree equal to 0, then the normalized Laplacian is just going to be the inverse of the degree matrix multiplied by the combinatorial Laplacian. So here you'll notice we divide the first row by 3, by 2. We divide by 5, not 3 here. So actually we don't get a 1 on the diagonal entry, but it's just by convention because we have a loop. And on the last row, we divide this row by 4. And the combinatorial Laplacian is interesting because one of my favorite theorems is the matrix tree theorem. And if you take the combinatorial Laplacian, take a submatrix, a certain submatrix, and take its determinant, you can count some interesting things. So let me just review. A forest is a graph so that the removal of any edge increases the number of connected components. And each connected component of a forest is a tree. So here's a forest, for example. A spanning forest of a graph, VE, is a forest VS, so it has the same vertex set, but its edges come from a subset of the edges of our original graph. And we say that a spanning forest is U-rooted for some subset of the vertices V if each tree has 1 root in U. A force, it's a spanning force of this graph because we just took edges from this graph and the vertices are exactly the same. You could say it's U-rooted if U is the magenta vertices, because a choice of roots is just a choice of vertex in each connected component. Then here's the matrix tree theorem. If U is a subset of our vertices and you delete the rows and columns corresponding to U from the combinatorial Laplacian to obtain a matrix, then the determinant of that new matrix counts the number of U-rooted spanning force. So for example, we take the combinatorial Laplacian of this matrix, delete the rows and columns corresponding to these magenta vertices. So now we have, since this has degree 3, we have a 3 here, degree 2, 2 here, 1 edge between them, -1, -1. Take its determinant, which we know is 3 times 2 minus -1 squared equals 5. And you'll notice that I've shown exactly 5 different U-rooted spanning force. And those are all of them according to this theorem. One corollary of this is if you know that the characteristic polynomial of any matrix is the sum of the principal minors of a certain size, then you can actually say that the characteristic polynomial of the combinatorial Laplacian has coefficients given by a combinatorial expression. So each coefficient ck, which is the coefficient of x to k multiplied by the sign, is the number of k-rooted spanning force, meaning u-rooted spanning force for some subset u of v, where u has size k. So remember, rooted spanning force is just a spanning force plus a choice of a vertex in each component, which we call the roots. So equivalently, we can take a sum over all spanning force with k components, but each such spanning force contributes the number of choices of roots, which is just, well, you can choose any vertex in each connected component. So you just multiply the sizes of each connected component. All right, so if I had this spanning force of some graph, to make a choice of roots, I need to pick one of 3 vertices for my root of this component and one of 2 vertices as my root for this component. So the weight of this force would just be 3 times 2, and that would be its contribution to this coefficient ck. So for example, again, take this graph and take its characteristic polynomial of the combinatorial Laplacian. This t to the 4 corresponds to this spanning force. It's not a very interesting spanning force, but if you multiply all the sizes of the connected components, you're going to get 1 to the 4, which is exactly the coefficient of French here. It's a 1. This 12 corresponds to the spanning force with 3 components. Well, if you think about them, those are in bijection with the non-loop edges. So it could look like this, it could look like this, plus the other 2 vertices here, 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 here. There are 6 of them, and each of them has a component of size 2. Then the remaining components are all size 1, so you have 2 times 1 squared, and I said there were 6. So add them all up, you get 12. And if you trust me, the spanning force with 2 connected components, if you sum up all these weights, you're going to get 45. You look at the spanning force with 1 connected component, namely the trees, and then you multiply by the weights, which should be 4 because there are 4 vertices, and you should get 52. So this is the same as saying there are 13 spanning trees. Okay, so one thing you can do with spectral graph theory, which is the study of these matrices associated to a graph, is try to do linear algebra with it. So we know that if A is an n by n real symmetric matrix, for example, the combinatorial Laplacian is a real symmetric matrix, then it has n real eigenvalues. Moreover, we can take a Rayleigh quotient. So if f is a non-zero vector in Rn, we define the Rayleigh quotient to be this, which is the inner product of AF and F divided by the inner product of F and F. And we know that this is always greater than or equal to the smallest eigenvalue of your matrix and always less than or equal to the largest eigenvalue of your matrix. And it's a little interesting to plug in A equals the combinatorial Laplacian. It turns out if you take the combinatorial Laplacian, then the numerator of this Rayleigh quotient is the sum over all edges of the square difference of f evaluated at those vertices. And of course, the denominator is just the sum over all vertices of f squared. When A is the normalized Laplacian, well, I said the normalized Laplacian in my notation was the inverse of the degree matrix multiplied by the combinatorial Laplacian. Actually, many authors take it to be this right here. because this matrix is actually symmetric. But for me, it's not that important because these two have the same eigenvalues, they're similar. But for the statement of this theorem, where I'm using Rayleigh quotient specifically for symmetric matrices, I guess we should try to use a symmetric matrix. So let A be the symmetric normalized Laplacian, then you actually need to do sort of a change of basis. So you multiply it by the square root of the degree, H vertex. And actually this Rayleigh quotient is still interesting. You can write it as the sum over all edges of the difference of f squared divided by the sum over all vertices of f squared multiplied by the degree. And if you want to be a little fancy, you can write this as an integral over all edges of, let's say the gradient is what's the difference at each edge. So I'm going to write that as gradient of f squared. And you want to integrate with respect to the counting measure. I say integration because, well, it's a sum and you can think of sums as integrations. And the denominator is an integral over all vertices. Again, it's just a finite sum of f squared with respect to the counting measure because I'm just adding them up. This is the same thing in the numerator. I have the gradient of f norm squared integrated with this counting measure. Denominator, I have an integral over all vertices, f squared with respect to a degree measure because I want to add each term multiplied by the degree of a vertex. So you can think of this as an integral with a different measure from the counting measure. Then the question is, what happens if I stick in different measures for the edge measure and for the vertex measure, other than the counting measure and other than the counting measure or the degree measure? So for edge measures, well, this is just edge-weighted graphs, and edge-weighted Laplacians have been studied a lot. If you change the vertex measure, then we're going to get, well, the theory here. So let VEW be a vertex-weighted multigraph consisting of a multigraph and a weight function, just simply assigning each vertex to a positive real number. And I'm going to define the inner product space L2V to be the space of all scalar fields or all functions from my vertices to real numbers, equipped with the inner product given by this integral, which is again a finite sum over all vertices of f at v times g at v times w at v. So for example, here, how I draw a vertex weight graph is I draw the graph, and inside each vertex, I write the weight. So this is the weight 1 vertex, this is the weight 3 vertex. And outside here, you see that I've put sub numbers next to each vertex. That's going to be my scalar field. So if this is f and this is g, its inner product is going to be given by 1, which is the weight, times 2 times 3. So 6 plus 1 times 3 times -1. That should be -3. Plus 2 times -2 times -2, which is 8. And the other ones should be 0. So the inner product between f and g is equal to 3 plus 8, 11. And this was integral of fg tw over all the vertices. A second inner product space I want to define is L2 of E, which is, you can think of the space of all vector fields. By vector, I mean associate to each edge a one-dimensional real vector space. And you think of a vector as either pointing towards one vertex and away from the other, or in the opposite direction, and those two are going to be negatives. Then the inner product is just, you take the dot product on each one-dimensional vector space, and then you integrate with respect to the countermeasure. So for example, I've drawn these vectors here. This is a vector of length 2 pointing from this vertex towards this vertex. And if I take the dot product 2 and 3, I should get a 6. 2 and 1, but notice they're in opposite directions, so I should subtract their product. So I should write -2. 0 and 1 is 0. 5 and 0 is 0. 1 and 1, again in opposite directions, is -1. So 3 is the inner product between f and g, which was the integral of f dot g with respect to the countermeasure over all edges. And there are going to be two interesting linear maps between these two spaces that I want to study. The first one is, I'm going to call it the gradient map. I already said that the gradient is sort of the difference at each vertex. I actually want to make this a map from a scalar field to a vector space, a vector field. So if you have a scalar field, which is just an assignment of real numbers at each vertex, take its difference, but create the vector pointing in the direction of steepest. So 1 minus -1 is 2. The magnitude should be 2, but it should point this way because 1 is larger than -1. Again, this is 2. Between -1 and -1, well, they're the same thing, so the difference is 0. Its gradient is 0. -1 and 2, gradient is going to be 3. 2 and 3, gradient is going to be 1, pointing towards the 3 because it's larger. And you'll notice I said it was a vector pointing in the direction of steepest ascent. So this is actually sort of an analog of the gradient from vector calculus, where you recall in vector calculus, if you have a vector field, you take a vector pointing in the direction of steepest ascent, that's the gradient. And there's another map I want to talk about, the negative divergence map, where if you have a vector field, you look at each vertex, you sort of sum the ingoing flow and subtract the outgoing flow, and then you sort of have to normalize by the vertex weight. So for example, going in is 1, going out is 2, so I do 1 minus 2, it's going to be -1, and I divide by the vertex weight, so I should get -1 here. Outgoing is 1 plus another 1, so that's going to be -2 divided by 1 here. Here I have incoming 1, incoming 2, so that's 3, minus 1, so it's 2, and then I divide by the vertex weight 3. Ingoing 1, subtract 3, so -2 divided by 2 here, and here is 3/1. So I just computed the gradient and the negative divergence. The reason I call it the negative divergence is this is a measure of how much of your vector field is sort of flowing into one point. So it's again an analog of negative divergence from vector calculus. So we can actually lift one more concept from vector calculus, which is the Laplacian. And the Laplacian in vector calculus is usually defined to be the positive divergence of the gradient, but because I get to make my own definitions, I'm going to take the negative divergence of the gradient from my definition of the Laplacian, and that's going to give me non-negative eigenvalues. That's really the only reason why I picked this. And the theories are the same, it doesn't really matter. So the vertex weight Laplacian is just going to be defined by the negative divergence of the gradient. And if you look at what this actually is when you compute it, it's going to be the inverse of the diagonal matrix with all the vertex weights multiplied by the combinatorial Laplacian. Which means that this actually specializes to both the combinatorial Laplacian and the normalized Laplacian. Is when your vertex measure is given by the counting measure. So W is the counting measure, which is 1 on each vertex. And this is the identity matrix inverse multiplied by the combinatorial Laplacian, get the combinatorial Laplacian. When each weight is given by the degree measure, then you get the degree inverse multiplied by the combinatorial Laplacian, and hence I get the normalized Laplacian, the non-symmetric version. Okay, one thing that's important for us is that this gradient operator and negative divergence are adjoint, meaning whenever I have an inner product like this, I can always move the gradient over to become a negative divergence, or I can move the negative divergence over to the other side equivalently and get gradient. Then the vertex weight Laplacian is actually self-adjoint, meaning that if I have an inner product like this, I can move the vertex weight Laplacian over to the other side. And you can see this just by moving the negative divergence to become a gradient here, move the gradient over here to become a negative divergence. And the reason I care about self-adjoint is because this is essentially the same as a real symmetric matrix. Meaning that any theorem you really have about real symmetric matrices, like having n real eigenvalues, or the theorems about Rayleigh quotients that I gave you before, they also all just apply to self-adjoint matrices. Okay, so what can we do with this vertex weight Laplacian? Let's define PGW to be the characteristic polynomial of the vertex weight Laplacian, multiplied by the product of all vertex weights. So it's a scaled characteristic polynomial. Then we actually get a weighted matrix force theorem, an analog of the matrix force theorem for the combinatorial Laplacian, for this vertex weight Laplacian. So each coefficient in this characteristic polynomial, multiplied by sign, can be given a combinatorial interpretation as a sum over all spanning force F with k components of the weight of F, where now the weight of F is just the product over all trees or each connected component in your forest. And the product is over the sum over all vertices in your tree of the weight at that vertex. So let me give you an example. We take this triangle graph with this vertex weight 3, 1, and 1 here. You notice I took the combinatorial Laplacian and I just divide the third row by 3. So I get this matrix here, take its characteristic polynomial, and it's going to be this divided by 3 by multiplied back by the product vertex weight. So this is my PGW. Okay, and if you look at the spanning force with 3 components, well, there's just one. It looks like this. And you look at the product of the vertex weights, that's going to be 1 times 1 times 3. That gives me my 3 here. If you look at the spanning force with 2 connected components, well, there are 3 of them. So in this connected component here, you sum the vertex weights, that's going to be 1 plus 3, that's 4. And then multiply the 1 contributed by this vertex here. So this gives me a 4. Same thing here, this is 1 times 1 plus 3. This gives me a 4. And here I get 1 plus 1 times 3. So that's going to be 2 times 3 is 6. And you know, this 4 plus 6 is exactly this 14 here. And one last example, well, you take all the spanning trees. Well, there's 3 of them, which I've listed out here. And the sum of vertex weights is 5, so these each contribute 5. And you know, this 5 plus 5 plus 5 is the 15 here. So the matrix force theorem generalizes to vertex weighted graphs. One interesting corollary about this is that we get a deletion-contraction relation. Deletion-contraction relations are interesting because they show up a lot. I mean, they show up for proper colorings, spanning force, spanning trees, the flow polynomial, chromatic polynomial, acyclic orientations. So what is deletion contraction? If you have a graph, G delete E is just the graph obtained by removing that edge. Very simple. To contract an edge E, so you have G contract E is what you get when you shrink along that edge and identify its vertices. So I shrink along here, and then I replace the 2 vertices here with the 3, with a single vertex. But we're talking about vertex weight graphs, so I want to make the vertex weight very special. And that choice of vertex weight is just going to be the sum of the vertex weights here. So this 2 and a 1 become a 3 in my contracted graph. Then deletion-contraction relation is a relation that expresses, you know, some invariant or polynomial about G in terms of that invariant or polynomial evaluated at G delete E and at G contract E. In particular, if E is a non-loop edge of my vertex weight graph, and we have PGW equals PG delete EW minus PG contract E, W contract E, where this is the weighting given by just replacing the new vertex weight to be the sum of the original constituents. So what's the proof of this? Well, remember each coefficient CK is the sum over all K component spanning force of this weight function on that force. And if you have a K component spanning force of GW, which doesn't use the edge E, and that's in bijection exactly with the K component spanning force of G delete E, which don't use the edge E, so that's all of them. And moreover, this bijection preserves all vertex weights, which means that the weight of each forest here just maps exactly to the weight of each forest here. What about the vertex? What about the K component spanning force that do use the edge E? Then they're exactly in bijection with the K component spanning force of G contract E, of G contract E, period. So these are in bijection with the K component spanning force of G contract E. And moreover, this bijection is weight preserving because if you sum the vertex weights in each connected component, well, if you're looking at the connected component that doesn't use this edge, then it's going to be the same, right? 1 plus 3 is still 1 plus 3. What about the connected component that does use this edge? 2 plus 2 plus 1 is 2 plus 3 because 3 was given by 2 plus 1. So again, the weight of the force goes exactly here. So you have a weight preserving bijection between the K component spanning force from GW to the union of G delete E, W, and G contract E, W contract E, which means that these sign coefficients are exactly the sum. So CK of GW is CK of G delete E, W plus CK of G contract E, W contract E. You stick in the sign and you'll get this deletion-contraction relation exactly. Okay, I want to tell you about the Cauchy interlacing theorem, which is useful because it's useful in linear algebra, and we're going to do linear algebra with our matrices, hopefully. So you can state like this: the most important application that I'm just going to need is if you have a real symmetric matrix and you take a subnet, then you get these inequalities on the eigenvalues. So for example, I've taken a real symmetric matrix here. I take this principal submatrix right here. And if you look at the eigenvalues, they exactly go lambda1 is less than or equal to mu1, less than or equal to lambda2, less than or equal to mu2, less than or equal to lambda3. That's Cauchy interlacing. So one thing you can show about this Laplacian is that if you delete an edge, the eigenvalues interlace. So this is just going to be the same as the proof for the combinatorial Laplacian. Whatever proof you can give for the combinatorial Laplacian, this interlacing relation, it sort of lives. So let lambda1, lambda n be the eigenvalues of GW, mu1 to mu-m, the eigenvalues of G delete EW. Then they interlace exactly like mu1 less than or equal to lambda1, less than or equal to 2, less than or equal to lambda2, mu-m less than or equal to lambda n. And let me just note that the reason people care about interlacing theorems is you have the eigenvalues of one graph, you want to modify it slightly, then you also want to ask, how do the eigenvalues of your new graph relate to your original graph? So this is sort of the idea of one way you can answer it is look at what happens when you delete an edge. And it turns out that the eigenvalues interlace exactly like this. So what's one way to prove this? All eigenvalues of this Laplacian are actually non-negative. So it suffices to show the lemma for the non-zero eigenvalues. You get the interlacing on the non-zero eigenvalues. You also get the interlacing on the zero eigenvalues. Okay, the edge Laplacian, let's define that to be the gradient of the negative divergence from your space of vector fields to itself. Is self-adjoint for the same reason the vertex wave Laplacian was self-adjoint. And we also know whenever you have matrices AB and BA, and these products are real symmetric matrices, or just have like all their eigenvalues intact, then these two matrices have the same non-zero eigenvalues with the same multiplicity. It's only the multiplicity of the zero eigenvalue that could be different. Okay, now take the edge Laplacian of G delete EW and compare it to the edge Laplacian of GW. If you write it in matrix form, you do have to take an arbitrary choice of direction for each edge if you want to write it in matrix. Then the edge Laplacian of GW looks like this. The edge Laplacian of G delete EW looks like you're just ignoring the contribution of one edge. So it looks like a principal submatrix, which means by Cauchy interlacing in the previous page, we get the interlacing on the eigenvalues of the edge Laplacian. And since these had exactly the non-zero eigenvalues of Laplacians, with the same multiplicity, you have the interlacing on the level of the vertex wave Laplacian. And that's the proof. So it's very slick. Okay, so it turns out if you take the Laplacian of GW, the Laplacian of G delete EW, and the Laplacian of G contract AW, contract E, and let their eigenvalues be given by lambda1 to lambda n, mu1 to mu-n, and nu1 to nu-n minus 1, respectively. And you get exactly the interlacing. Mu1 is less than or equal to lambda1, less than or equal to nu1, less than or equal to mu2, lambda2, nu2, all the way until nu-n minus 1 is less than or equal to mu-n, less than or equal to lambda n. For example, let this be my vertex wave graph. G delete E, where E is the magenta vertex, looks like this. G contract E looks like this. And the eigenvalues are given right here. And you'll notice it goes exactly 0 is less than or equal to 0, less than or equal to 0, less than or equal to 5 minus root 10 over 3, less than or equal to 5 over 3, less than or equal to 5 over 2, less than or equal to 5 plus root 10 over 3, less than or equal to 3. And what's one way to prove this? Well, recall that we have this deletion-contraction relation. And if you write it in terms of the eigenvalues, just factor your polynomials P, G, W. Then there's some positive real numbers A, B, C, so that you have this relation, A times T minus lambda 1 all the way to T minus lambda n equals B times T minus mu1, T minus mu-n equals C times T minus mu1 all the way to T minus mu-n minus 1. If there's a shared root psi of both GW and G delete EW, then just divide both sides of the equation by T minus psi. Because if you know that T minus psi is a factor here and T minus psi is a factor here, T minus psi must end up being a factor here. So you divide both sides by the equation and you just want to insert it later. And then, so for example, if we take the lambda 1 to the lambda 3, mu1 to mu3, you'll notice that we have a repeated, you have a shared root. Actually, all Laplacians have eigenvalue 0. So you can just get rid of them because you know that there must be a new equals 0. Actually, it's new 1, but so you can get rid of them, and then you can just consider this part. Finally, when all they're distinct, you apply the intermediate value theorem. Because, for example, if you just evaluate at lambda 2, well, you know that lambda 2 vanishes this product. And you also have the interlacing between the lambdas and the mu's from the interlacing for the edge for G and G delete E, which means that you can calculate the sign of this thing. So we know that there's exactly one mu that's larger than lambda and one that's less than. So this is negative. So if this was 0 and this was negative, and this term here must be, I want to say, negative. So you know that at lambda 2, that this polynomial PG contract E, W contract E, divided by the T minus size is negative. And if you do the same thing at mu 3, you know, it vanishes here. You know that this must be, I want to say, you know, I don't really know the signs too well, but I want to say this is negative, then it must be positive here. And then by the intermediate value theorem, you must have a root mu in between lambda 2 and mu 3. And you just do that. And then you insert back in the mu's that we removed, and you get the interlacing exactly as we wanted. So there's a root here, and there was a root because we had a shared root 0, 0, 0. Okay, so what can we actually do with this beyond just, you know, edge deletion and contraction? We can just crank it up a notch. So there's an interlacing between G, G delete E, G contract E. If you just take the interlacing between G delete E and G contract E, then that's like you have a graph. I'm not going to put in the vertex weights, and you take any two vertices you want and you just smush them together. And also you need to add the sum of the vertex weights, because you could think of it as there being a phantom edge here, G being the edge with the edge added. G contract E is what happens when you smush it back. So you use that interlacing relation, and you can get Groen-Marist and Sunder's result for interlacing for the combinatorial Laplacian. The reason being, the combinatorial Laplacian is the version of the vertex weight Laplacian, and all vertex weights are 1, right? So you want to understand the relation between the eigenvalues of this vertex weighted graph to this vertex weighted graph here. One way you can do it is contract this edge. You get vertex weighted. You get a vertex weighted graph here with vertex weight 2. That was 1 plus 1. And then you sort of uncontract this edge using this relation here. So this 2 splits into this, and you can show that the eigenvalues of this disjoint union is actually just the union of the eigenvalues of this graph and this graph. So you end up getting a relation between the eigenvalues of this graph and this graph as you want it here. And of course, you can actually now just generalize this to something beyond what Groen-Marist and Sunder had, just by taking, you know, asking what happens if you contract a lot of vertices at once. You contract them all together, and you do the same thing of getting rid of vertex weights here. You get an interlacing relation for the combinatorial Laplacian when you smush vertices together. Well, for the normalized Laplacian, when you delete an edge for the normalized Laplacian, you're asking what's the relationship between the eigenvalues of this graph, this vertex weight graph, and the eigenvalues of this vertex weight graph, where the vertex weights are given by the degrees. Well, you can think of this as unsmushing this graph into these two graphs, the disjoint union of these two graphs. So you can relate the eigenvalues of this graph to the eigenvalues of this graph just by using the interlacing we had. And the reason it works is because if you smush together the sum of the degrees on one part and the sum of degrees on the other part, ends up being the sum of degrees in the smush graph, right? So this was degree 1, this was degree 1. You put it together, you get degree 2, and that was exactly the sum of these vertex weights. So you get this interlacing relation. Butler extended the result of Chen, Davis, Hawley, Patel, Stewart by asking what happens if you delete a subgraph. Well, you just do the same thing. You do the same unsmushing argument, and then you relate the eigenvalues of this vertex weighted graph to this vertex weighted graph. And actually, we improve the result of Butler whenever you delete at least one vertex using our method. Another question is what happens when you smush vertices together for the normalized Laplacian? Well, actually, that's exactly the smushing argument that we give. So we get to recover, Chen, Davis, Hawley, Tell Stewart's result, and Butler's result for what happens when you just do this operation on the normalized Laplacian. Is you're just summing the degrees, and that's just the degree in a new vertex. And here's where using the convention that the degree of a loop is 2 is important, because this edge should contribute 1 and 1 here. In the smush graph, I wanted to contribute 1 plus 1. So each loop has to have degree 2 for this to work. One last thing that we can try is ask what happens when you delete a subgraph for the normalized Laplacian. And we want to try doing this, unmerge, unsmush argument again, but we're not allowed to have vertex weights of 0 in the current formulation. So we can just write, we want to relate the eigenvalues of this weighted graph, this weighted graph. Well, we can unsmush, but write this as 1 minus delta, 1 minus delta, delta here, again, interlacing relation whenever delta is greater than 0, and just take the limit as delta goes to 0. And we'll get a relationship between the eigenvalues of this graph and this graph. So this is a new result that we can get. Okay, so I think I have time to talk about this. Recall that the edge Laplacian is the gradient of the negative divergence, which is self-adjoint and has the same non-zero eigenvalues as the Laplacian or the vertex weighted Laplacian. Call the kernel the cycle space. It's spanned by closed curves, meaning if you just take a closed walk like this, and then you have a 1 in each direction, you sum them up, then that's going to be in your cycle space, and your cycle space is spanned by these things. And call its orthogonal complement cut space. Actually, the cut space consists of what you can think of as conservative vector fields, because if you think about it, these are exactly the vector fields such that when you take this path integral on a closed curve, then you always get 0. So it's kind of an analog of a conservative vector field in vector calculus. Anyways, because we're taking the orthogonal complement of the kernel, then the eigenvalues from the cut space to the cut space when you restrict the edge Laplacian are exactly the non-zero eigenvalues of the edge Laplacian, which are exactly the non-zero eigenvalues of the vertex weighted Laplacian. Okay, and it turns out there has been, these cycle spaces and cut space have been studied before. There's one interesting paper where, conservative vector fields show up implicitly. And that's in this nice paper of Brooks, Smith, Stone, and Tutt, which says that every square tiling of a rectangle, so you see this is a rectangle and you tile it with these squares, this length 6, length 4, length 5, so on, corresponds to a circuit diagram with poles plus and minus. You have a vertex for each horizontal segment, and then you just draw an edge for each square. Okay, and it turns out that this circuit is a conservative vector field, because if you integrate along each loop, well, it's a circuit. So by, I don't know, it's either Kirchhoff's first law or second law, your integral will be 6 plus 1 minus 3 minus 4 equals 0. Because you're just taking the difference in voltage, and that's always going to be 0 at a point, right? So there is a nice way to use this interesting correspondence. If G is the graph corresponding to a squared rectangle, let's say with A and height V, and let U and V denote the poles, and lambda 1 to lambda n denote the eigenvalues of GW, where you just have any vertex weighting W. Then lambda 2 is less than or equal to this weird expression is less than or equal to lambda n. So how do we do this? Let's compute the Rayleigh quotient of this vector field. We already said that it was in the cut space. So it's we're taking the Rayleigh quotient of this vector field with respect to the edge Laplacian restricted to the cut space corresponding to the circuit. And we know that's just edge Laplacian of F inner product with F over F inner product with F. Move the gradient over to become a negative divergence. Inner product of divergence of F, negative divergence of F over inner product of F and F. Remember it as this integral. Okay, what is the negative divergence at each point? Well, let's look here. It's 6 minus 1 minus 5. Here it's 4 minus 3 minus 1. Actually, again, because one of Kirchhoff's two laws, by some conservation of some physical thing, it's 0 at all of the interior nodes. So actually, this is a sum of a lot of zeros, and you do need to ask for the contribution at each point. So at U, the outgoing ones are 6, 4, and 5. And then you need to divide by the vertex weight. So it's asking essentially for what is 6 plus 4 plus 5, and then you divide by the vertex weight at at U squared, and then you need to multiply by W. So the question is, what is 6 plus 4 plus 5 squared? Well, the side length was 6 plus 4 plus 5, so I can write this as just A squared over the weight at U. And you do the same thing for the weight at V. So that's the numerator. It's this nice, interesting thing. So what is the integral here? Well, you just need to add 6 squared plus 4 squared plus 5 squared plus 1 squared plus 3 squared plus 1 squared, 5 squared, 4 squared, 6 squared. And there's an easy way to do that because all these are squares. And turns out it just corresponds to the area of this rectangle, which is A times B. So you end up getting A squared over weight of U plus A squared over weight of V over AB, which is this thing here. And we know from our interlacing that this is always lesser to the largest eigenvalue, always greater than or equal to the smallest eigenvalue. Well, so why shouldn't this be a lambda 1? It's because in a Laplacian, it turns out the lambda 1 is always 0. And we're using the edge Laplacian because this was a conservative vector field, so we can skip all the way to the first positive eigenvalue, which if it's connected, it's lambda 2. And that ends up giving you this cool result here. Okay, Brooks, Smith, Stone, and Tet were actually more interested in squared squares, right? So squared tilings of squares. So the question is, let's say I have a graph here, some graph, and I really hate this edge for some reason. I want to get rid of it. And the way I get rid of it is by replacing this edge with a squared square. So what I mean by that is replace it with the graph corresponding to the squared square. What can we say then? It turns out that the eigenvalues between these two graphs exactly interlace. So here I have an edge here. I replace it with the squared squared corresponding. This squared square, which corresponds to this graph. So it's not a very interesting squared square, but I chose it because it was small. I replace it with this graph, and the weights are anything you want, as long as the weights of the original vertices are preserved. So 1, 1, 3. This vertex could have any weight you want. And you'll notice the eigenvalues exactly go, I want to say mu1 is less than to lambda 1, less than or equal to 3 minus root 2, less than or equal to 5 over 3, 2, 3, 3 plus root 2. And if you want to know like what's the relation between this result and the result I gave you two slides ago, you can sort of do the same thing for, you can do the same thing for rectangular tilings of rectangles, except now you have to go to a edge-weighted version of the Laplacian as well. And you'll sort of see that a rectangle collapses to a rectangle, which means a rectangular tiling graph collapses to a weighted edge, and you can get a result like that. Okay, let's skip to a application of this Laplacian. So let me review what the chromatic number is. If you have a graph G with vertex set V, a proper coloring of your graph is just an assignment of positive integers from your vertices to positive integers. So that if two vertices are joined by an edge, they must be given different assignments or different colors. So for example, you could think of blue as 1 and magenta as 2 here. This is not a proper coloring. They're joined by an edge, but they're given the same color. This is fine. Different colors, even though they're joined by an edge. So the chromatic number chi-g is the least positive integer k, so that there is a proper coloring, sending v to the numbers from 1 to k. So what's the minimum number of colors you need to get a proper color or such a satisfying assignment? And we can show that if G has m edges and lambda n is the largest eigenvalue of your vertex weight Laplacian, then chi-g is greater than or equal to lambda n over lambda n minus 2m over weight of v. Again, we have an edge-weighted version of this. Okay, how do we do this? You take your graph, which might look like this. You take a proper coloring using exactly as many colors as you need. So you use the chromatic number of colorings. And then once you have this coloring, we're going to do something fun, and that fun thing is let's assign to each color a kth root of unity. So we could think of this as I, -1, -1, +1, +I. Then take the Rayleigh quotient of this thing. Well, I define Rayleigh quotients for real vectors, but you're allowed to use complex vectors as long as you sort of do this same thing on the real part and on the imaginary part. So you take the Rayleigh quotient of this thing. It's always less than or equal to lambda n. But the Rayleigh quotient of this thing, this assignment is not necessarily easy to compute unless it's, unless it's like a nice assignment somehow. And two, it might not be very good if, for example, it might not be very good if two colors that, have edges between them very often have a small distance between them a lot. So we can instead use the expected value of this Rayleigh quotient by just taking all permutations of the assignments of your roots of unity. And it turns out once you do this and rearrange, you're going to get this thing. And this, when you restrict to the combinatorial Laplacian, you get a known result. So this is the largest combinatorial Laplacian eigenvalue, and this is the average degree. Restrict to the normalized Laplacian, also known result. This is your largest normalized Laplacian eigenvalue. So it's an interesting argument to recover these two results here. Yeah, this was the picture, except I think I put on the wrong slide. Okay, one last application. There's a chromatic symmetric function that I want to define. So this is a definition by Stanley, 1995, and it's also a definition by Crew and Sperkel. I want to say 2020, or in here right now, with the vertex weights. So Stanley studied the non-vertex weighted version, Crew and Sperkel added the vertex weights. So if you have vertex weighted graph, so you need your vertex weights to be positive integers in this case now. The chromatic symmetric function is just this generating function. You sum over all proper colorings of x color v1 to the weight of v1, x color v2 to the weight of v2, all the way to x color vn to the weight of vn. And there's a nice conjecture dating back to Stanley's original paper that the chromatic symmetric function distinguishes weight 1 trees. That is, if you have two weight 1 trees, they have the same chromatic symmetric function, then they must necessarily be isomorphic. So for example, if you take this weight 1 tree, well, all proper colorings are just an assignment to integers, so that this is a different positive integer for this one. So it's x1, x2 plus x2, x1 plus x1, x3, x3, x1, and so on. Okay, one thing you can show using our deletion-contraction is that weight 1 trees with equal chromatic symmetric functions necessarily have the same combinatorial Laplacian eigenvalues. And it's really easy to show just by induction. We want to show that there's a linear map sending each chromatic symmetric function to the polynomial PFW for each weighted force. Then you do induction on the number of edges. You know that G is equal to G delete E minus G contract E, where G delete E and G contract E are both weighted force. You take your map, since you have it on the base case, and you're doing induction, you're going down one step. Then since this map is linear, it sends exactly XFW to PFW at that number of edges and so on. So since you have this linear map, it means that you can recover the Laplacian, the vertex weighted Laplacian characteristic polynomial, the scaled version, from your chromatic symmetric function, which means that for weight 1 trees, you can recover the combinatorial Laplacian characteristic polynomial and hence its eigenvalues. But obviously this doesn't kill the conjecture, because McKay, for example, in 1977, gave a nice method of constructing infinitely many Laplacian cospectral trees. In fact, I think he showed that the limit of trees, of the number of trees that aren't Laplacian cospectral to anything else, goes down to 0 as n goes to infinity. So it's, it's partial progress. And there is also one more way to, one more
you have,
I want to talk about. Yeah.
Okay, you have less than 2 minutes.
It's fine. It's like okay. A half a minute. And that's a way to construct Laplacian cospectral graphs. If you have two non-isomorphic graphs with an edge f and f prime, so if you delete an edge F and F prime that they're isomorphic. So you notice if you delete this, and you delete this, they're isomorphic. Contract this and contract this. They're isomorphic with the vertex weight, right? So it's an isomorphism with the vertex weight. They know that since Laplacian is G delete E minus G contract E, and they must be Laplacian cospectral. And this was an argument showed to me by Wang and crew at the UVC discrete map circle for a different related polynomial. So yeah, that's how you can construct Laplacian cospectral graphs in deletion contraction. Thank you.